Hey guys, it is 4/29 Wednesday. Welcome back. This week we're going to be doing the second part of a lesson on acids and bases. We have about 2 more parts to go. So hopefully you got my email, and the first thing that you should have actually done is complete a virtual lab. If you weren't able to find that, I'll show you in just a second what you should do. So last week, we kind of dipped a toe into what indicators are and what the pH scale is and what that means for acids versus bases or alkaline substances. And we're going to kind of move beyond indicators this week and talk a little bit more about properties. So I have a question for you all. What happens when you pee in a pool? So I found this graphic on the chemistry of swimming pools, and there's a lot of information here. I think that we all know that chlorine has a lot to do with the chemistry of swimming pools. But what I found specifically is this little section here, pee in the pool and chloroamines. And so it says that ammonia or ammonia-like compounds found in human sweat and urine actually react with hypochlorous acid, which is just, like an acid found in pool chemicals, and it produces what are called chloroamines. It is not these, not chlorine, sorry, it is those, not chlorine, that causes the characteristic smell of swimming pools. And so down here it says peeing in the pool helps to produce more trichloroamine because there is acid present in your urine called uric acid. And that acid reacts to produce certain types of chlorine. And so the more pee in the pool, the more pungent the chlorine smells. I also found this little graphic. 2 of my best friends own a pool store. And so they deal with pool chemistry a lot. And if the pH level of your pool is not where it needs to be, you have to try to neutralize it a little bit by adding acids or bases. So if you want to lower the pH of your pool, meaning make it more acidic, you need to add more acidic substances. But if you want to raise the pH of your pool and make it more alkaline, you need to add more basic substances. Okay, so checklist for this week. Before you're watching this video, you should have participated in a virtual lab. If you are unable to do that, you need to let me know somehow, email, remind, or Schoology. So if you have not done that yet, I'm going to have you pause the video, because what you should be looking at first is on Schoology. In today's folder, you will see a link to a virtual lab on properties of acids and bases. If you click that link, it should just pop up here, and you'll just go ahead and hit next. If for some reason this link doesn't load, I'm going to ask that you choose this little box with an upright arrow. That will open it in a new tab, and you'll be able to go through the virtual lab this way. It's pretty self-explanatory. You'll kind of drag some things around and test the pH and identify substances as acids or bases. It's important that you do that before you go any further in the video. For the rest of this week, I'm going to share a video lesson with you. This is a little bit longer of a lesson because there's a lot of intro material to share with you on acids and bases. So while the video and the possible note-taking that you do during this video is a little bit longer, I have shortened the choice activities. So hopefully this is still not taking you more than 2 hours, but I do anticipate this week will take you longer than next week. So after we go through the video notes, there's nothing other than the virtual lab that you had to do before tuning in here. Choice activity is literally going to be either attend a Zoom meeting or do the questions on your own, and then the quiz is posted up through Sunday. So before we begin, today's lesson, I have provided you with an outline. So if you are taking notes, that will be helpful for you when it comes back to the quiz, because although this is based on topic 10 in the review book, I don't go in the same order that the review book does because I don't really like that order. So what we're going to talk about today are the properties of acids and bases and how to identify substances as acids or bases. So section 1, we're going to talk about the reaction of acids and bases with indicators like litmus, phenolphthalein, and universal indicator. We're going to talk about section 2, how they react with metals. Section 3 is a little bit more complex. How acids and bases dissociate, we're going to define that and talk about what it means to be an electrolyte, and 2 acid-base theories for how to identify substances as acids or bases. Lastly, we're going to talk about how acids and bases react with each other. I'm going to demonstrate what a neutralization reaction is, and then an introduction on titrations, which is a lab procedure. I'm just going to introduce you to the equation because next week is going to be all about titrations. So section 1, acids and bases, a property that they have is how they react with indicators. So in the virtual lab, you saw that for something to be considered acidic, using litmus, litmus turns red in an acidic substance. Whereas bases are going to take that litmus and they're going to turn it blue. So when it comes to litmus, acids are red and bases are blue. When it comes to a second indicator, phenolphthalein, this is an indicator that we're going to use in a lot of lab procedures like a titration. Phenolphthalein is colorless until the pH gets to be about 8. So what that means is that anything acidic or neutral is going to be colorless or clear, whereas anything above a pH of 8, so 8, 9, 10, 11, all the way through 14, pink indicates that a substance is a base. It has a high pH. The pH scale for universal indicator we saw last week when I did my demonstration, and this pH scale represents the colors in universal indicator, and it's kind of nice because it almost matches litmus. So the acidic range is here for universal indicator, kind of a Roy G. Biv kind of color spectrum. Neutral is really going to be more of your greens, and then anything that's a base is going to be blue to purple in universal indicator. Property number 2 is how acids and bases react with metals. When it comes to acids versus bases, acids, according to the virtual lab, are the ones that react with metals to form kind of like bubbles or gas. This one's not that hard to remember because acids react and bases and neutral substances do not react with metals. This goes back, way back to when we talked about table J. If a metal is more active than hydrogen, which is typically found in acids, it will form a chemical reaction. So for example, HCl was the acid, one of the acids that you identified in the virtual lab. When it reacted with zinc, which zinc is more active than hydrogen, zinc kicked hydrogen out all by itself as a gas and formed a new substance. That is only specific to acids, and we'll get into that more because pretty much anything that involves hydrogen gas or hydrogen ions is going to be related to acidic substances. Bases and neutral substances, no reaction with metals. Okay, so now for the little bit complex portion of the lesson. How acids and bases dissolve or dissociate gives them a lot of properties. So we have talked about this term electrolyte in the past. So I'm going to focus here first on how do acids and bases dissolve. If acids and bases, when dissolved in water, meaning an aqueous solution, if that allows their ions to move freely, It is classified as an electrolyte, meaning a substance that conducts electricity once it is dissolved into solution. So if you look over here, this acetic acid has positive and negative ions moving in solution. That conducts electricity and lights the light bulb. If ions cannot move or they do not dissolve into positive and negative ions, then they will not conduct electricity. So one thing about acids and bases is they are both electrolytes. Now, quick quiz question from days of yore. What other types of substances other than acids and bases were also classified as electrolytes? A, ionic compounds or salts, B, covalent compounds, or C, metallic compounds? Take a minute. Which of the following conduct electricity when they dissolve in solution? Well, one clue is this guy over here that I didn't talk about. KCl, potassium chloride, has a high conductivity. That is classified as A, an ionic compound or a salt. Ionic compounds are electrolytes. Covalent compounds, like sugar, are not. And metallic compounds, although they conduct electricity, they do not dissolve into solution. So A, ionic compounds and acids and bases are all electrolytes. So this other term, dissociation, I just want to talk for a minute about what this means. If we look at something like water, H2O, dissociation of water just basically means how it breaks apart into solution. And it's kind of strange to think about water breaking apart in solution because water typically is the solution. But if you have something like H2O, it can break apart into two ions. A hydroxide ion, which is OH, that's a negative ion, and an H plus ion, which is a positive ion. The fact that water dissolves or dissociates this way gives it a lot of interesting properties. The same can be said about acids and bases. HCl was one of the acids that we identified in the virtual lab. HCl is really just an ionic compound that breaks apart into two ions, H plus and Cl minus. And I apologize, I wrote those backwards to what the equation is up top. That's how it breaks apart or how it dissociates. Sodium hydroxide, which we're going to learn is a common base, NaOH, is really just another ionic compound that splits apart, kind of like water, into two ions, Na plus and OH minus. So dissociation literally just means in solution, how does that ionic compound break apart? Water's kind of our base because it's not an ionic compound, but the way that it dissociates kind of dictates our definitions of acids and bases. When you watched the video last week, you were talking about ion dissociation without even really knowing it. So hopefully what you got out of it is that that atmospheric CO2 contributes to the ocean chemistry. When CO2 reacts with water, it forms this acidic substance called carbonic acid. So now taking this one step further, why can I classify that as carbonic acid? Well, I could test it with litmus and it would turn red. I could react it with zinc and it should bubble. But based on this new property, how it breaks apart is going to dictate why it's classified as an acid. Since it breaks apart into hydrogen ions, and which are positive, and negative ions, which are these carbonate ions, that is one definition of why it's a base. So let's kind of get into that with this hydrogen ion theory. There are two theories we're going to discuss that you can use to really define whether a substance is an acid or a base. The first theory is the Arrhenius theory, and the second theory is what's called the Bronsted-Lowry theory. So let's start with the Arrhenius theory. When we saw HCl dissociate into H plus and Cl minus in solution, according to the Arrhenius theory, this is an acid because all Arrhenius acids dissociate into H plus ions. So what that means is, in solution, the only positive ion I'm going to see in an acid is H plus. There are no other positive ions, so it's an acid. On the flip side, when a base, or a substance that we're going to classify as a base, dissociates into two ions, the only negative ion I'm going to see is hydroxide. So going back to the previous example here, why is this not a base? Because it doesn't have OH minus ions as its only negative ion, but it's an acid because of the H plus. NaOH is a base because it dissociates into hydroxide as the only negative ion in solution. So I want you to maybe pause the video or just kind of take a look here. I have 5 different substances listed on this page, and I want you to identify each one as either an Arrhenius acid or an Arrhenius base. I'll do the first one with you. H2SO4. When H2SO4 dissociates, it's going to break apart into 2 ions. And I can write this 2 ways. I could get real fancy and I could say it breaks apart into H plus, and then what's left over, HSO4. I'm assuming that that's going to be a negative ion. It would not have been wrong if you had told yourself, okay, it breaks apart into 2 H pluses and an SO4 minus. I'm going to use this one. Either way, when I look at this, the only positive ion in solution is H plus. The negative ion is not hydroxide. Therefore, this is an Arrhenius acid. Pause if you haven't already done so and try the rest. CaOH2 dissociates into Ca plus 2 and 2 OH minus ions. This positive ion is not hydrogen. This negative ion is hydroxide. Calcium hydroxide is an Arrhenius base. HBr breaks into H plus and Br minus. Positive ion is H plus. HBr is an Arrhenius acid. Same with HF. H plus and F minus. No hydroxide. H plus is the only positive ion in solution. HF is an Arrhenius acid. And last but not least, KOA dissociates into K plus and OH minus. This is not hydrogen. Oops. K plus is not hydrogen. OH is hydroxide. KOH is an Arrhenius base. So basically, if you see H, it's an acid, and if you see OH, it's a base in most cases. Before we move into the next theory, I want you to make a connection here. If I were to draw a hydrogen atom, the nucleus of a hydrogen atom contains 1 positive proton, and in the first orbital, 1 negative electron. And we know that all atoms have to be neutral, so they have 1 of each. But when we're talking about dissociating into a hydrogen ion, if it is an H plus ion, that implies that it has lost this electron. So what is a hydrogen ion really? Is just a proton. So moving forward, even though a hydrogen H plus ion is just an ion of hydrogen, an atom that has lost one electron, they are the same thing as protons. Now, why do we care? The second theory about defining an acid or base beyond just if it has H plus or OH minus in it is what's called the Bronsted-Lowry theory, and this can get a little bit confusing. A Bronsted-Lowry base is something that is classified as a proton acceptor or an H plus acceptor. So what that forces me to do is this might not be something that's clear cut where it has an H and an OH in it all the time. So this equation that I have for you, NH3 and water react to form these two products. I know something in here's got to be a base because I see OH minus at the end, but determining whether my base is NH3 or H2O can be difficult. So the first thing I'm going to do is I'm going to match up what I think goes with what from beginning to end. So I think like this NH3 kind of becomes this NH4 plus. And this H2O will kind of become OH minus. Those are what are called conjugate pairs, and it's just kind of matching up what looks alike from beginning to end. What happens to this NH3 from beginning to end? It gains an H. I also could say that it accepts an H. What happens to the H2O? It loses or donates the H. So according to the Bronsted-Lowry theory, the NH4 is the Bronsted-Lowry base. A Bronsted-Lowry acid is the opposite. So the Bronsted-Lowry acid is something that donates or loses an H. So here's a different equation for you. I would match up, well, okay, HCl becomes Cl minus, and H2O becomes this new thing, H3O plus. So let's first look at what happens to HCl from beginning to end. The HCl loses, or we could say donates, its H, it's gone. Whereas the H2O seems to have gained one or accepted the H. So what would be my Bronsted-Lowry acid is just what loses the proton or the H plus from beginning to end. In this case, the HCl is what loses or donates its H from beginning to end. Now, if I go back to the first equation, if NH3 is the proton acceptor, that means that the water is the donor. And you're going to see that there is an acid and a base pair in every reaction. So if NH3 is the base, that meant H2O was the acid, the acceptor versus the donor. In the second example, if HCl was the acid, then that means that this water molecule in this equation was the base. Here's another example. The first thing I want you to do is match up what you think goes with what from beginning to end. So what goes with the HNO3? What goes with the H2O? I would have matched up HNO3 with the NO3 minus, and I would have matched H2O up with the H3O plus. So that's step one, what goes together. Step two, what happens to the HNO3 from beginning to end? Does this gain or lose an H? hopefully you chose that HNO3 loses its H. And instead of the word lose, this theory uses the word donates. What happens to H2O from beginning to end? Hopefully we see that H2O gains an H to become H3O+. And instead of the word gain, this theory says that it accepts NH. So according to my definition, if HNO3 donates the hydrogen ion, it is the acid. And if H2O accepts the H, it is the base. So we use these terms accept or donate protons or H+ ions. Now let's talk about water for a second before we move on, because water can be both, and this kind of gets into why water is neutral in the first place. So if I just have water in solution, that water can either gain an H or it can lose an H, and I could have chosen either one to pair it with. So I want to ask you, if I call this water molecule 1 and water molecule number 2, the way that I have them matched up here, which one is my Bronsted-Lowry acid and which one is my Bronsted-Lowry base, and why? So again, number 1 becomes H3O+, and let's say number 2 becomes OH-. Hopefully, we are looking and seeing that water molecule number 1 gains an extra H. That means that it's the proton acceptor, and it is the Bronsted-Lowry base. Water molecule 2 loses or donates its H, so I would call that the acid. All right, feel free to watch that part again, or tune in for the Zoom meeting this week, and I will explain that in better detail. Okay. Last property of acids and bases is how they react with each other. So acids and bases react with each other to form an ionic salt and water, and this is the basis for what we call a neutralization reaction. A neutralization reaction has this basic general formula. So if you see something you know to be an acid added to something that's a base, you can figure out that it will produce always a salt and water. And why this is called a neutralization reaction is because salts and water have neutral pH levels. So this kind of goes back to pool chemistry. If your pool is too acidic, you add a base to neutralize it. If your pool is too alkaline, you add an acid to neutralize it. Here's a couple examples of acids and bases reacting with one another. All of these, I'm going to kind of use the Arrhenius acid definition and kind of forget about Bronsted-Lowry for a minute. HCl, that breaks apart into H+, that's my acid. NaOH breaks apart into hydroxide, that's my base. So acid plus a base has to produce some kind of salt and water. Where am I going to find the water? Well, water is H2O. I got that from here and here. So what's left? Salt, NaCl, here and here. Try number 2, KOH plus HF. Which one's the acid? Which one's the base? I see OH, so that's my base. I see H, that's my acid. How am I going to get water out of this? Well, H and OH, which means my salt is K, potassium, and F for fluoride. Last example, HBr, that's my acid. NaOH is my base. I know a neutralization produces water, so that's that H and that OH. And then I'm left with Na and Br for my salt. So those three are all neutralization reactions. Quick quiz question. Acid and base reactions, neutralizations, are also considered what type of chemical reaction? Do these look like synthesis reactions? Do these look like B, decomposition reactions? Or C, double replacement? D, single replacements? Am I making one thing? Am I breaking down one thing? Am I swapping two ions? Or am I swapping one ion for another? Neutralizations are also C, double replacement reactions. Okay, last but not least, we're only going to do like 1 or 2 examples of titrations, because next week I just want you to know this basic equation and I'm going to have you actually do a virtual one. Acid-base titrations are lab procedures where we can use this idea of neutralization reactions to determine unknown volumes or concentrations, which are molarities of acids and bases. On table T of the reference table, you have this general equation. So basically, we're going to always be looking for one variable in this equation. M stands for molarity, which is a concentration. A for acid, B for base. V stands for volumes, in milliliters usually, of A, acid, or B, bases. So here's an example. Suppose you want to know the concentration of HCl being dumped into a river near a factory. In order to do so, you take 10 milliliters of that HCl and you test it with 25 milliliters of a 1 molar NaOH solution to determine the concentration. This is going to be my answer when all is said and done, but I want to show you this setup. M of A, molarity of A. I need to know that HCl is my acid. That is going to be my missing variable. I don't know the concentration of HCl or acid. Do I know the volume of acid used? Yes, I do. 10 milliliters. I can set that equal to my base values. The molarity of my base, and I have to know that NaOH is a base based on my properties, is 1.0. My volume of base is 25 milliliters. So to solve for molarity of acid, I can divide both sides by 10 milliliters. And when I plug that into my calculator, 1 times 25 equals, divided by 10, I get that the molarity of my acid is 2.5 molar. Here's a second example. So pause and try this one on your own, and then this will be the last of the notes for today. Suppose you want to know what volume of 1 molar acetic acid is needed to neutralize 15 milliliters of a 0.5 molar calcium hydroxide. So I know that I have acetic acid. It has acid in the name. I know I have calcium hydroxide, and hydroxide means it's a base. So I just need to figure out my knowns and my unknowns. Molarity of acid is 1.0 molar. I want to know the volume of acid that I need to complete this titration or this neutralization. I know I have 0.5 molar base, calcium hydroxide, and the volume of base is 15 milliliters. divide both sides by 1, and let me know what you get for your volume of acid. I got 7.5 milliliters. All right, now I know that's a lot. So your choice activity is going to be pretty straightforward. This is going to be in the review book. You have the option of completing the work independently and just sending me a photo of the questions that you've completed. Or I'm going to be hosting a Zoom session today at 3 o'clock. You must have watched this video and attempted or at least read the questions before participating. If you can't make the video, I'll try to record it and post it. So I'm either going to know that you sent me a photo of your independent work, or I'm going to see you at the Zoom session this week. Here are the questions that I'm going to ask you to do from the review book, and I have scanned a document onto Schoology in case you don't have a copy. In part A, on page 189 to 191, you're going to do 11 multiple choice questions. In part B, you're going to do 2 multiple choice questions. And then part C, you're going to do 2 short response questions. So make sure that you have done everything and checked out those questions before you tune in. Expectations for those of you attending the Zoom meeting. I'm going to send the code via the Remind app 15 minutes prior to the meeting. Do not share the Zoom code with anyone who is not in our class. Only log in as yourself and behave respectfully at all times. When you log in, mute your microphone when you're not speaking and turn on your video so that I can mark your attendance. All right, that does it for this week. Reach out if you have any questions. I know that this was a long one, but hopefully now we can kind of go shorter from here and do some more virtual acid-base lab activities. Have a great day.